And because the
So
process.
you're supposed to write it in terms of Berkovits and Pauli matrices?
Yes, I know that's the answer, but I don't see why.
Sorry?
I know that's the answer, but I don't see why. I don't know how to specify this.
So try to do it inductively. Try to do it n equals 1, n equals 2, n equals 3, and then you'll try to see a pattern. That's the way I would do it. So it doesn't repeat every n, but I think it repeats every 2n. So if you do it once, n equals 1, n equals 2, n equals 3, I think that's enough to get the whole pattern. Okay, so last lecture we talked about word line and worldsheet supersymmetry. The rest of the following 2 lectures will be about space-time supersymmetry. So of course it's the same algebra. It's just now we're reinterpreting the P. Instead of acting on the world line or worldsheet, P will now act in space-time. So it will be the usual space-time momentum. But it's the same algebra. So these gamma matrices, just to remind you, gamma 0 is choose a basis so that it's 0, 1, minus 1, 0. And the other one will be with these Pauli matrices. So A, of course, goes from 1 to G minus 1. So each of these blocks, remember, are just the vial spinners, and these are the anti-vials. These are the different chiralities. Okay, so we're going to start by doing d equals 4, which is, of course, relevant for the standard model if you want to supersymmetrize it, or from anything. So we have xm. Pauli matrices. So in this case, we're going to split the alphas. So of course, in 4 dimensions, there are 4 different components. So there are 2 here and 2 here, which are the 2 different chiralities. So we'll call them alpha and alpha dot. This is 1 to 2. This is 2-component notation, which is convenient. Of course, you could use the 4-component notation, but then you would have to use the full 4x4 gamma matrix instead of the 2x2 Pauli matrix. So these, for sigma 0, is just going to be defined to be 1, 0, 0, 1. And the other ones are the usual Pauli matrices. Using these Pauli matrices, it's easy to see that these gamma matrices satisfy the usual anti-commutation. Okay, so in this case, we have 4 supersymmetries. The alpha has 4 components. Furthermore, a fermion, the minimal dimension of a fermion, will have 4 components. But remember, if you have an action for a fermion, only half of the components are on shell. So it's easy to see. You can write the fermion action in terms of these Pauli matrices. So this is, I'll split also the fermions into these chiral and antichiral. So this would be antichiral, this would be chiral. And I forgot to do. So this would be a massless fermion. So these are all what are called Majorana fermions. They're not Dirac. So they only have 2 physical degrees of freedom. If you want to put a mass term can be written as 2 components. important notation. So this is the notation of Wesson-Bagger. The idea is that these indices, they go from 1 to 2, and you can raise and lower them using the epsilon. So I can put the indices up or down, but unlike the vector indices, which are raised and lowered using the Minkowski metric, these indices here are raised and lowered using just epsilon alpha beta, which is, of course, this antisymmetric matrix. Okay, are there any questions? Okay, so the equation of motion is obviously sigma m. We get it by varying psi bar alpha dot. So this is going to be equal to I m. So you can see that the two components of psi bar are known once you know the two components of psi beta. So although there are 4 degrees of freedom, either 2 complex or 4 real, depending on how you count, you can see that they're related. So there are only 2 on shell. Real. Now, of course, the electron has 4 real degrees of freedom because the electron is a Dirac fermion. You have the electron would spin up, or spin plus a half, the electron would spin minus half, and the positron would spin plus a half, and the positron would spin minus half. If it's Majorana, it would turn out that the electron and the positron are the same particle. A Majorana fermion can't carry charge. Okay, so this is the action for the minimal, the smallest representation. So you see there are 2 degrees of freedom. So supersymmetry means that, of course, we need also 2 bosonic degrees of freedom. So the minimum action we can construct, which is supersymmetric, needs these 2 bosons. So the simplest case is where the 2 bosons are just a complex scalar. So phi and phi bar are complex conjugates. And of course, you just have the massive Klein-Gordon. Now it's easy to show that this equation of motion implies that psi satisfies the equation of motion. This implies this, and of course also from psi bar. So of course phi and psi have the same number of degrees of freedom because we could have written this with psi bar also, but the 2 are related. So there are only 2 fermions with mass squared m, with mass squared m squared, and 2 bosons. Okay, so suppose we have the sum of these 2 actions, S equals SB. Of course, we're not guaranteed we have space-time supersymmetry just because we have the same number of bosons and fermions at equal mass level. We have to check that the action is space-time supersymmetric. So we have to construct the space-time supersymmetry transform. So what I will do, I'll use the language delta as being the space-time supersymmetry right here. Delta is the space-time supersymmetry generator. And I'm going to define it this way. So in 4 dimensions. Well, so in general, it's this. So this is bosonic. This is the fermionic parameter. And this is the generator. Okay? So this language is convenient because now you treat this just as an ordinary bosonic transformation. But the parameter is fermionic. So what you can show is that delta 1, delta 2, if I commute 2 supersymmetry transformations, I will obviously get something proportional to C1 and C2. So this is going to be equal to the commutator of C1 alpha Q alpha with C2 beta Q beta. So we have two different supersymmetry parameters. And now we can use this algebra. So it's a little bit, you have to anti-commute this to here. And this is going to be an exercise. This is going to be equal. Yes, please.
Why do we put plus psi bar times Q bar?
This is the definition of delta.
Yeah, but why put like plus psi bar times Q bar?
Oh, because I'm doing here the general dimension. I haven't even, nothing for it. Okay, so, I just want to, so you're going to get, this is equal, I don't promise the factors as always. This is going to be equal to, get me 0. Times n. And there might be a factor of 2 that I'm missing. Probably usually there's a factor of 2 here, and a factor of 2. In any case, this is something you can check. So exercise 1 is finding the coefficient. Okay, so this is, of course, this object here is now a bosonic parameter, which is the bosonic parameter of the translation. Well, this is another way to describe the supersymmetry algebra, which is convenient. Okay, any questions? So now in the four-dimensional case, it was already pointed out, this alpha goes from 1 to 4, but now we're going to go to this two-component notation. So I'll tell you what the transformations of phi and psi are. The transformations of phi is equal to C alpha and psi alpha. Transformation of phi bar is going to be equal to C bar. So this should remind you of what we did yesterday with d equals 1 and d equals 2 supersymmetry. The boson transforms into the fermion without derivatives. On the other hand, the fermion, psi alpha, is going to transform into the boson with derivatives. So it will be I. Times dn phi. So now, of course, you have indices here because you have more than one component. So this is without mass. If you put the mass term in, you get another contribution. So this is the transformation of psi, and similarly, psi bar is a complex number. So now you just check. If you do this transformation, you want to check that this bosonic action will, of course, not be invariant. It will involve transformations of phi, which will turn into psi. But it will be canceled by the transformation of SF. Now, of course, we can check that the algebra is preserved. We can compute delta 1, delta 2, phi. That's trivial. Okay, delta is equal to delta 1. Delta 2 of phi is just C2 alpha psi alpha minus delta 2 of psi 1 alpha psi alpha. And now you need to be careful because this is bosonic, this is fermionic. Remember, this is bosonic, not fermionic. So we can just commute it through. So this is equal to C2 alpha of delta 1 of psi alpha. Delta 1 of psi alpha we just get from here. This is equal to I sigma n alpha alpha dot psi bar alpha dot 1. 1 because this delta 1 times dm phi minus m phi bar. I forgot this is C2 alpha. C2 alpha, C1. Now we're supposed to do it in the opposite order, this second term. So just the same thing minus switching 2 with 1. Okay. Now this term is going to be two terms. So this is equal to I psi 2 alpha sigma n alpha alpha dot psi bar 1 alpha dot minus psi 1 alpha psi n alpha dot psi bar 2 alpha dot. So all we did was just subtract, so switching 2 to 1 times dn phi. And then you have this term, minus n phi bar psi 2 alpha psi 1 alpha minus psi 1 alpha psi 2. Okay, it's almost what we want. What we want is this. Because this is going to reproduce this up to a coefficient that I didn't. So this thing should vanish. Well, let's check that this vanishes. So psi 2 alpha, psi 1 alpha, we have this definition of what the raising and lowering means. So we can write this as epsilon alpha beta, psi 2 beta, psi 1 alpha. So that means this here is just the difference of this with this. So this term here is equal to, let me just check, minus, is equal to this thing minus C1 beta, C2 alpha. But now epsilon alpha beta is antisymmetric. So I can write the first term as the needless space. Let's do it over again. So C1 alpha, C2 alpha minus C2 is equal to epsilon alpha beta, C2 beta, C1 alpha minus C1 beta. This term here is antisymmetric, so I can put the minus sign and switch, if I switch the alpha and beta. Okay, the minus sign came because alpha and beta is antisymmetric and alpha and beta. But now remember, these are Grassmann coordinates. So this is equal to plus C1 beta, C2 alpha, which is obviously canceling that. Okay, so this term drops. Okay, so we've shown that at least when acting on phi, the supersymmetry algebra is preserved. Acting on phi bar is essentially the same computation. When you act on psi, you find that it's not quite 0, but it's equal to this thing here, I dm psi alpha, that's the term we want, plus a term which vanishes using equations of motion. Precisely as what happened in the t equals 2 case. So what that means is that the supersymmetry algebra only closes using equations of motion, which is obvious because we have 4 off-shell fermions and we only have 2 off-shell bosons. The way around that is to introduce auxiliary bosons like we did in 2 dimensions. I'm not going to do it, but you can do it. So in 4 dimensions, there's no problem in making all the supersymmetry manageable. Okay? You introduce an auxiliary boson, which doesn't properly.
The fermionic parameter, what's the difference between C1 and C2?
They're 2 different parameters. So let's consider the bosonic case first because it's less confusing. Suppose you do 2 translations. I can do them in 2 different directions. One translation, then I do another one. So they're 2 different, just 2 different, this could have, the first one could be 3.5, the second one could be 4. Okay? So they're just 2 different fermionic parameters, you can also choose different fermionic parameters. So they're just not the same. That's the only thing, that's the only label 1 and 2. So there are two different supersymmetries.
It's like a measure of how much you transform a boson.
That's right. So I can't tell you it's 3.5. 3.5 is, but it's the same idea.
Can you write eager?
Can I write, sorry? Bigger, yes. There's some seats closer too. Okay, any other things?
When you quantize these kind of actions, these kind of systems,
Yep.
you just establish by separate. You separate bosons of fermions and you establish conjugators with bosons and anticonjugators.
So that's one way to do it.
Uh-huh.
But when you have manifest supersymmetry, there's a better way to do it. So the better way to do it is to put phi and psi into a superfield. So just like what we did, I didn't do it, but at least I told you about how to do superfields in 1 and 2 dimensions. In 4 dimensions, you can do the same thing. So you combine the field I'm calling phi and psi into a superfield that's called capital Phi, which has the following type of structure. And now instead of quantizing phi and psi independently and computing Feynman diagrams independently for phi and psi, you can, in the 4-dimensional case, you can compute Feynman diagrams directly for capital Phi. So you compute Green's functions, Wick contractions of phi and phi, and compute Feynman diagrams in superspace. Now this is useful because, as I told you in the last lecture, there are cancellations that come between the bosons and fermions in the loops. And if you use this superspace, the cancellations are manifest. Now, unfortunately, this is possible in 4 dimensions, but when we go to higher dimensions, it's not known how to do this. Precisely because we don't know the auxiliary fields, which are necessary in order to make the supersymmetry manifest. But when the supersymmetry is manifest, yes, that's the best way to do it. Any other questions? Okay, so this is one example. This model here is called the Wessamino model. It was the first example of 4-dimensional spacetime supersymmetry. And just for historical reasons, it's useful to point out that this 2-dimensional example I gave yesterday is the first example of supersymmetry in the literature. At least if you're not Russian. I mean, there's a Russian version, which some people say is supersymmetry, some people say it's not. I don't want to go into history. And this 4-dimensional model is the first example of 4-dimensional supersymmetry. So actually, supersymmetry was, quote, discovered theoretically from string theory. Okay, any questions about this model?
I have a question. When you put in the covariant manifest the action, you need some auxiliary fields.
Yes.
So this makes basically the model, I mean, one can think the model like the fermions are interacting with the scalars.
So, okay, this is a free model. Now we can do, that's right, you can add about interaction. So let me, since this question came up, I'll tell you what you have to put in an auxiliary field and its complex conjugate, because you're missing 2 bosons. Okay, and now this superfield here has another term, which is quadratic in theta, which couples to f of x. And now you can write the actions in terms of this phi. So the actions are of the type phi, phi bar, theta. And then you can have terms which are functions, more complicated functions of phi, phi bar. And you can also have terms which only depend on phi and not on phi bar. These are called D terms for people who know. These are called F terms. There's a whole thousands of papers on how to use these to construct actions. But for example, if you just put in a term here of the type phi cubed, so phi squared is just the mass term. And you can put in a term phi cubed, and that generates a quartic coupling. And the coupling involves not just bosons with bosons, but cubic couplings of bosons with fermions. So you could do it, of course, without having manifest superspace, but then you would have to work harder to check if the interactions preserve supersymmetry. Any other questions? Okay, so this is one example where you have a scalar, complex scalar, and a spinor. Now we can do a second example in which we still have the spinor, but we're going to have a vector, a gauge field. Now, of course, in 4 dimensions, a massless vector has 2 degrees of freedom, because photon has 2 degrees of freedom. So another supersymmetric action we can add, construct is just FMN, FMN. This would be super Maxwell. And of course now it has to be massless because the photon is massless. So this is now a second type of supersymmetric action. So I haven't proven it supersymmetric, but at least it might be because you have 2 physical bosons and 2 physical fermions. So now I have to tell you what the supersymmetry transformations are. And they'll be slightly different because now I have boson, which is a vector. So although it transforms into the fermion without derivatives, it does it in a slightly different way. So it involves this Pauli matrix. And you need to get the vector.
But does the transformation, how you define the transformations later?
How do you know what the right transformations are?
When you introduce the S term, do those transformations change?
When I introduce the which term? The
Yes.
math?
The auxiliary field.
Yeah, so when I introduce the F term, so if you remember I wrote down the case with masses, so the Western minimum. Let's go back to the Western minimum. In that case, I had a term in psi, I think I erased it, which was of the type I sigma m alpha dot psi bar alpha dot dm phi, and then I had a mass term which was minus m phi bar c alpha. Now this is funny because the supersymmetry transformations should not involve the parameters in the Lagrangian, right? This should be anything I want. The supersymmetry transformation should be independent of the parameters in the Lagrangian. Once you put in the auxiliary fields, these parameters disappear. So this becomes, once you put in auxiliary fields, this is replaced by this field I call F bar. So yes, the supersymmetry transformations change once you put in the auxiliary field. And all the parameters from Lagrangian drop out. Any other questions? Okay, so let's go back to super Yang-Mills, or super Maxwell. So this is a transformation of the gluon by the photon, and plus the complex conjugate. Plus I. And again, the transformation of the fermion is going to involve derivatives of the gauge field, but it has to involve only gauge invariant objects, because this is not gauge invariant, AN. So it can transform into psi, that's fine. The gauge non-invariant object can transform into a gauge invariant object, but the converse cannot be true. A gauge invariant object has to transform into a gauge invariant object. So it has to transform into FMN. Transformation is FMN. Sigma m, sigma n. So this is the product of 2 Pauli matrices. So if you contract the dotted index, this has a structure of this type times psi beta times, sorry, xc beta. And the other one is just a complex number. was a question?
Why should it be?
Independent of the parameters.
Okay. So you want the supersymmetry transformations to be manifest. So what does manifest mean? It means that they should not depend. So you should be able to write down any action you want, and supersymmetry should be present as long as the action is written in terms of these superfields. So it's like if Lorentz transformations depended on the mass, then you would know that Lorentz transformations were not manifest, because if you change the mass, you'd have to change the Lorentz transformation. So this is similar. Any other questions?
All the time these are Majorana fermions or not necessarily?
So let me just remind you. So in 4 dimensions, if you start with the minimum dimensional representation has 4 components, which you can either think as 4 real components or 2 complex components. So if you think of them as 2 complex components, then you call it the Weyl fermion. If you think of it as 4 real components, then you call it the Majorana fermion. But what it's not is 4 complex components, which you would call the Dirac fermion. So why these have these names? Historical reasons. But so you can either call it the Weyl fermion or a Majorana fermion, but not the Dirac. Yes? Yeah, so in Western Bagman notation, they put a bar on it. I just avoided it, but so it's the Hermitian conjugate.
The dotted index of the second circle should be down, right?
Thank you. Yes. So again, this with up index, you just get it from the one with down indices by raising and lowering with the epsilon. So Western Bagman would put a bar on it, but for me, it's just as you raise it.
Yes. And could you repeat, please, how do you arrive to these equations?
The supersymmetry transformation?
Yes.
I did not tell you how I got them. All I did is I wrote them down, and I claimed that the algebra satisfied by these is going to give you this. If once you write the fields in terms of superfields, then essentially the supersymmetry transformations are given to you once you write this structure down. But in this case, I started from the opposite direction. I wrote the actual components and then just told you what these are. So unfortunately, when we go to higher dimensions, that's the only way to proceed. We don't have a general procedure for constructing supersymmetric actions in higher dimensions. In 4 dimensions, we can use this superspace. But when we go to 10 dimensions, for example, we just have to work hard or guess and see if it works. This is big enough? This is big? Okay, so now in 4 dimensions we have 2 nice examples. We have the scalar model and we have this vector model. So you can either have this is called Super Maxwell. The first case was called Wessamino model because they were the first ones to write it down. Now I want to do the general case. We could do it in 4 dimensions, but we might as well do it in any dimension. So as we'll see, the relevant issue is not the dimension; it's the number of supersymmetries. So we will see that theories with the same number of supersymmetries essentially look the same in every dimension. Okay, so are there any questions about 4 dimensions before we do the general case?
Wait, what was that? So something that's supersymmetric with 4 supersymmetries looks the same, equals 4 or 2 or...
It looks similar. It has the same number of fields. Of course, instead of depending on 4 x's, it would only depend on 2 x's. But we will do an example where you'll see, if you start with the case in 4 dimensions, I can immediately tell you what the case is in 3 or 2 dimensions. Okay, so suppose we have Q alpha, where alpha goes from 1 to r. I don't even have to tell you the dimension. I'm just going to tell you how many supersymmetries I have. And of course, it satisfies this algebra. So there are two relevant cases, and this is real components. Okay? So there are two relevant cases, which is going to be m squared non-zero and m squared 0. The number of fields and states in the theory depends if it's massive or massive. So we'll do m squared first case. In this case, we're going to choose Lorentz frame. We're just interested in counting states. We're not interested in writing covariant Lagrange. So we just want to know how many states we have so we can choose a reference frame where P0 is non-zero, so this is equal to n, and all the other P's are 0. So in that case, this algebra just becomes Q alpha, Q beta is equal to delta alpha beta. Well, if I divide Q by square root of m, square root of 2m, this is just the Clifford algebra. It's precisely the same algebra we saw on Monday. So the way we find the states in this is we split these Q's into things we call B minus and B plus. So alpha, R is always even. So this is always an even number, so you can split it just into pairs. So let's call them Q1 plus IQ2, Q1 minus IQ2, 1 over square root of 2. So we could call this, let's call it A plus, this is called A minus 1. And then, okay, the last one would be 1 over square root of 2, Q to R minus 1. R. Similarly. And we'll call this A, I guess, R over 2 plus an A R over 2. And these satisfy precisely the same algebra. Let's set m equals a half, just to simplify. These satisfy the same algebra as the B's. We divide this by m. Probably it's the same algebra. So we have A plus J, A minus K, just equal to delta. Okay, so now we know what our states are. They're just minus plus R over 2 of these. The only question is if they're complex or real. Now, what you would like is that the complex conjugate of plus 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 is equal to minus 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 minus. But now we have to be careful because Q changes the statistics. If it was boson, acting with Q is a fermion. So before acting on this changed the chirality. Now it changes the statistics. So if you have an even number of plus and minus signs, if R over 2 is even, which is not the case here, if R over 2 is odd, this is impossible. Because this is a boson and this is a fermion. So when R over 2 is odd, you get twice as many. So you have 2 to the R over 2 plus 1. Because it has to be complex. So these are the number of states. If R over 2 is even, if there was only one of these, then this would be fine, because this is a boson, this is also a boson. So in this case, you have 2 to the R over 2. Now these states, of course, are half bosons and half fermions. So in this case, you have 2 to the hour over 2 bosons, 2 to the hour over 2 fermions. In this case, you have 2 to the hour over 2 minus 1 bosons, 2 to the hour over 2 minus 1. So for example, in 4 dimensions, R was equal to 4, R over 2 is equal to 2. So this is, you have 2 bosons and 2 fermions. This is precisely what we have. We have the phi and phi bar and the psi. So this is the massive case. Now we do the massive. Okay, any questions?
Another question. Could you repeat the reality conditions?
Repeat the what?
Repeat the analysis of reality conditions.
Yeah. So in the spinor case, acting with a Q changed the chirality. In this case, it changes the statistics. So if I try to say that this is a real representation, then the complex conjugate of this would have to be this. Now, if you have an even number of plus signs, both of these are bosons. So it's consistent. But if you have an odd number, there's no way this can be the complex conjugate of this because one is a boson, the other is a fermion. So you need twice as many states. That's why it's plus 1. Any other questions? Okay, now we'll do the masses case. Now in this case, the reference frame you want is not P0 equals M. You can't, there's no mass. But you can choose P0 equals P1 equals the energy. And all the others, P2 to P to B0. Now in this rest frame, you can choose gamma 0 to be here. And let's choose gamma 1. You can always choose gamma 1 to be equal to this. These anti-commute. This squares to 1 and this squares to minus 1. So in this case, the algebra is Q alpha, Q beta is equal to 2 times, so again, when this is 0, you get the identity. You get P0 times 1, 0, 0, 1 plus P1 times 1, 0, 0, minus 1. But these are equal, so this is just equal to 4 times the energy times 1, 0, 0, 2. So what this means is that half of the Q's, if you anti-commute, they anti-commute with everything. So that means Q1 to Q R over 2. These objects satisfy the same algebras as before, but the other ones, Q R over 2 plus 1, QR, these all essentially you can ignore because they anti-commute with everything. So the states are constructed just from these. So now we do the same analysis. We split these up into complex pairs. But now instead of having R over 2, you have R over 4. So let's suppose R is a multiple of 4. If R is not the multiple of 4, we have to do some more work. But let's suppose, for example, in 4 dimensions, R is equal to 4. And the interesting cases we'll do is always R is a multiple of 4.
Sorry, why do you construct only with the first pair divided by 2?
So these generators here, they satisfy the property they anti-commute with everything. So it's consistent to set them to 0. We're looking at the minimal dimensional representation. Okay. So we can set them all to 0, and the only thing we cannot set these Q's to 0 because they satisfy this algebra. So the first half of the Q's, they have to act on the state. They can't just annihilate the state. But these, we can consistently say that they annihilate all the states. If they don't, you have bigger representations. But we're looking for the smallest Okay, so we have now 2 to the power over 4. So now we have the same question. Is this real or complex? Now, if r over 4 is odd, then obviously that has to be complex for the same reason. So r over 4 being odd means you have 2 to the r over 2.
It's not over 4.
I'm sorry, this should be r over 4 thing. So this is, for example, in d equals 4, or in this case, r is equal to 4, so r over 4 is equal to 1. So this gives me 2 to the 1 plus 1, gives you 4 states, which are the same as before. So we have 2 to the r over 4 boson. 2. That's correct, 2 bosons and 2 fermions. That's what we got for the massless case, for example, supermass one. Now, if r over 4 is even, there's a chance that the representation is real. So r over 4 even it can either be real or pseudo-real. And in fact, the analysis is precisely the same as we saw for the spinners. So, depending on the number of pluses here, so obviously it has to have an even number of pluses. But now, if it has just 2 pluses, so this would be the case r equals 8. What you want to say is that this object here is real. If it were real, it would imply that plus plus is the complex conjugate of minus minus. Now, for the people who did the analysis in the spinner case, they found that this led to a contradiction. Remember, this was the case of g equals 5, 1, the spinners. You had a 4-dimensional Euclidean space. If you try to use this implies, of course, that plus plus double square is equal to minus. So you get the contradiction. So in this case, actually, r equals 8. You find that it has to be pseudo-real. So the way to classify these is if r over 8, if r over 4 is even, but r over 8 is odd, you find that the representation is pseudo-real. Where if r over 8 is even, so for example, that would be the case where you have plus 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 plus. In that case, you find that this is actually equal to plus this. So when it's pseudo-real, so we have these 3 cases. We have r over 4 odd. That always doubles the number of states. It has to be complex. We have if r over 4 is even, there are 2 possibilities. Either r over 8 is odd or r over 8 is even. If r over 8 is odd, it turns out the representation is pseudo-real. Using precisely the same analysis we did for spinners. If r over 8 is even, it's real. So in this case, where you have, for example, 16 supersymmetries, you have precisely 2 to the r over 4. Whereas here you have 2 to the r over 4. So you always get this doubling, except if r over 8 is even. Okay, so that's the number of states depending on the number of supersymmetries. So this is the minimal dimensional representation in any dimension. Okay? So we just need to know how many supersymmetries, and these formulas, if the representation is massive or massless, And these formulas tell you how many states you have. Okay, so now, of course, the next thing to do is example. Are there any questions? Okay, so the mathematics is very similar to what we did in Monday. I mean, it's not, I think it's important to remember the result. The derivation is not so important, but the special cases are the cases where you have 16 supersymmetries or 32 supersymmetries. Those are the ones in which you don't get this extra doubling. And those turn out, those are called maximal supersymmetries. Okay, so now we're going to discuss, these are the formulas, but now we're going to discuss examples. So up to now we did 4 dimensions, and we did super Maxwell. And one can ask, for what dimensions can we generalize the super Maxwell action? So of course the Maxwell action, any questions before I erase?
One, but it's a bit different.
Say it and then I'll decide if I have time to answer.
Okay. I've heard sometimes that the number of supersymmetries you can put on a space depends on the dimension because of some consistency.
Yeah, so we'll see that above 11 dimensions there will be no consistent supersymmetric theories. So we'll see that in a second. Any other questions? So obviously, if you only have 4 supersymmetries, you have to be in a dimension in which the minimal representation of a spinor is 4. You can't have 4 supersymmetries in 10 dimensions because the minimal amount of components of a spinor is 16. Okay, so that's one obvious thing. But you could ask, for example, well, suppose I have 500 supersymmetries. What kind of theory can I construct? And it turns out you cannot construct a physically sensible theory. For more than 32 supersymmetries, nobody knows how to construct a physically sensible. You get multiple copies of graviton. Okay, so what I'm going to do now is discuss the highest dimension of super Maxwell theory or super Yang-Mills theory that we can construct, which is supersymmetric. So this is trivial to find because we know we need an equal number of bosons and fermions. So super Maxwell has the following in any dimension. Obviously Maxwell has the full minus. And we're going to construct a fermionic term, which obviously has to be massless. So this Pauli matrix is the same thing as I was calling here sigma m. So this is the action in any dimension. Now you can ask if it's space-time supersymmetric. And obviously to be space-time supersymmetric you need as many on-shell bosons as fermions. So the number of bosons is fixed. The number of bosons is just d minus 2 because you have a photon in dimension d. You always have one gauge degrees of freedom and one is annihilated by the equation of motion. So you have d minus 2 polarizations which are physical. Well, what about fermions? Well, that depends on the representation. So remember I was calling R the number of components of the spinor. So the number of fermions is not equal to R because R is the total number of components. It's only R over 2. Because on shell, half of the components of a fermion vanish. So this is equal to R over 2. So now one can ask in which dimensions are these equal? And it turns out they're equal if d is equal to 3, d is equal to 4, d is equal to 6, and d equals 8. Now, R goes like 2 to the d. So as you go higher than d equals 10, there's no chance of these two being. Okay, so d equals 3. Of course, R is equal to, give you the computation, R is equal to 2, R is equal to 4, 8, 16. So these are the dimensions in which this action is space-time supersymmetric. So it turns out in these dimensions, you can choose these matrices to be symmetric. And they actually satisfy a certain property, which is only true in these dimensions. Which is the following property. You contract the vector indices and symmetrize in the first three spinor indices, you get 0. This turns out to be related to the fact that if you, instead of doing 3, 4, 6, 10, you do 1, 2, 4, 8. This turns out to be related to the fact that division algebras. So for people who know, I don't have time to say what they are, but there are 4 division algebras, the real, complex, quaternion, noctonion, and these are related to these, to this identity in these dimensions. So there is a relation which, it's mathematics, but maybe some people think there might be some physics. Okay, now the supersymmetry transformations are the following. So it's almost identical to what we had in 4 dimensions. But of course, I did not split into alpha and alpha dot. This is go over alpha beta goes to n 0 to b minus 1. Alpha goes from 1 to 5. Okay, so this is the action, the super Maxwell, in any of these dimensions. And these are the supersymmetry transformations. And an ambitious exercise, you'll have to use these identities to show that delta 1, delta 2 is satisfies. On shell. So you will have to use these identities, and obviously the equations of motion also. Okay, any questions? Okay, so let me ask one more time. Any questions? Because I still have a few minutes or no?
Yeah.
Okay, so, but it's more important for me to answer questions than it is for me to cover more material. So are there any questions about things I've said up to now? Okay. So what we're going to do now is do the largest dimensional case. So d equals 10. So that's, of course, relevant to the superstring. This is 9. And we have the supersymmetry transformation. And the first non-trivial thing to do is we can generalize it to super Yang mills. So this is...
Sorry, I just wrote it up. In the variation for psi,
Yes?
is that, is that a beta on the, where the sigmas are?
Let me tell you what these are. So sigma m can be in either a matrix with up indices or down indices. And this sigma n is this object here. So why I put up or down indices? Because when you write this M matrix here, you can either have the matrix here or here.
I think you're just pointing out that the free index should be beta, not alpha.
Beta, oh, sorry.
I have another question. Shouldn't the variation of the fields depend on some parameters? For example, the variation of A depends on the determinate parameter psi. whereas
thank you.
the variation of psi.
Yes, thank you. Any other corrections?
Just one small question. This alpha and alpha dot indices, they are constructed out of the spin representation, but
Yes.
they are not viral spinors, or
Alpha is vial and alpha dot is antiviral.
all right.
So alpha and alpha dot was just in the four-dimensional case. Yes.
All right, thank you.
The conventional case, you choose the spin
Yes.
That's in order to match the.
So I always choose it to be the minimum dimensional representation. So four dimensions, the minimal representation. Okay. So the first non-trivial thing to do is to generalize to superangular. So I assume everybody knows what bosonic angular would be. So that's easy to do. Just put a trace here. And now FMN, all of these objects are now objects taking values of the Lie algebra. Also this fermion. So Ti are generators of the Lie algebra. So these sit in the adjoint representation. But these transformations are unchanged. This derivative here, of course, changes now the covariant. So now this is an interacting Lagrange. Cubic terms here, coupling the gauge field to the psi's. And of course, there are cubic and quadratic terms in FMN, because FMN is now the full non-abelian field stream. And now the last thing we want to do is discuss dimensional reduction of this to four dimensions. And we're going to get an action which still has 16 supersymmetries. So up to now, when we're in four dimensions, we only considered actions with four supersymmetries. But of course, you can have more supersymmetries. And when you dimensionally reduce, you don't break any supersymmetries. So,
Sorry, one question. Why does it have to be the adjoint representation? Is there some reason?
say it again.
Is there some reason why you have to use the adjoint representation and not
Yes.
fundamental or some other?
So Yang-Mills is necessarily in the adjoint representation. And supersymmetry has the same number of bosons and fermions in every representation. So there'd be no way to write this transformation if this was not in the adjoint. So you're forced that the super partner is always in the same representation as the original field. So it's not QED, for example, which has photon is no charge, the blue one is no charge. It's also not QCD, where the quark is in the fundamental and the blue one is in the adjoint. So this is a new kind of thing. Okay, so what happens when we do dimensional reduction? So I'll start the story now, but I will finish it tomorrow. So we have to decompose the field. So just because we're going to use both 4-dimensional and 10-dimensional indices. I'm going to do capital N, from 0 to 9, and capital A is 1 to 16. And then we're going to have 4-dimensional indices. M is 0 to 3, and alpha 1 to 2, alpha dot. And we're going to need one more kind of index, so I'll tell you in a second. Suppose the fields are independent of case, this action here is equal to an action just d4x times the volume of the six-dimensional space that you compactify it on, times some Lagrangian, which comes from dimensional reduction of these fields. Okay, so how do these fields dimensionally reduce? Well, obviously there are 10 different components of A, n, and there are 16 different components of psi A. So these are going to decompose into 4 components of a 4-dimensional gauge field and 6 other components, which will be scalars under 4-dimensional Lorentz transform. So let's call them 5. So let's say J is 1 to 6. These will decompose in a different way. So they split up, and I think I'm not going to be able to finish talking about this today. I'll just tell you the answer, and then tomorrow we'll discuss it more. These split up into 16 components. But what happens when you decompose a spinor is that when SO91 decomposes to SO31 times SO6, the spinor of SO91 decomposes into the product of a spinor of SO31 and a spinor of SO6. A spinor of SO6 has 4 components. It's a, if you go back to this, it has 4 complex components, which I'll label with A. So this A index goes from 1 to 4. If you remember, SO6 has 4-dimensional representations, but they're complex. So this will be the complex conjugates with an A down. And this alpha and alpha dot are the SO31 indices. So this is alpha alpha dot. And this is A. I could have called it A bar. But, okay, maybe I should. Maybe that's better notation. So A equals 1 to 4, and alpha is 1 to 2. So here are my 16 fermions. Here are my 10 bosons. And now I have to write the Lagrangian. So it turns out this J index, which is a vector of SO6, I can also express in terms of these A and A bar indices. It turns out that phi J, I can write something which is antisymmetric in these SU4 or SO6 indices. So since A equals 1 to 4 and B equals 1 to 4, if I anti-symmetrize, there are 6 different components here. And it turns out that I can also write it in terms of A bar, B bar. It turns out to be A, B, C, D, phi, C bar, B bar. So, okay, so this is something about SO6 that I will discuss in more detail tomorrow. But the punchline is that you can write this now in terms of these objects here. And then there's also coupling phi. This type. So we'll see all this tomorrow. Finally, the coupling of phi to the size. So this Lagrangian here is called n equals 4. E equals 4. And it has 16. So this n equals 4 signifies it has 4 times as many as the minimal amount. Okay, so this is what we'll discuss tomorrow. Okay.
This dimensional reduction does has to do with some kind of spontaneous supersymmetry breaking?
No. So what we're doing is we're just assuming that the fields don't depend on 6 of the directions. So for example, we compactify on some 6 circles. but we haven't broken any supersymmetry. Now, you can break supersymmetries, for example. You can say that instead of the field being periodic when I go around one of the circles, it's antiperiodic. That would break supersymmetry. So it's not spontaneous. You're doing it by changing boundary conditions. So there are ways to break supersymmetry which are related to dimensional reduction, but this dimensional reduction I haven't broken anything. All the supersymmetries. I've broken Lorentz invariance, because obviously once I dimensionally reduce, I don't have any more the full SO91. I just have SO31 times SO6. But I haven't, all 16 supersymmetries are still there.
And what kind of consequences you have once you have broken Lorentz invariant?
The theory is no longer SO91 invariant. I'm not sure. I'm not sure what you mean by consequences.
Yeah, me neither.
Okay. Any other questions?
What about the higher modes of the dimensional reduction?
Okay, so I've assumed that the fields are independent of this.
Yeah, but
if you don't assume that, then you'll have more terms here, and you'll have massive states associated with those groups of client states.
Even though the supersymmetry is all in the lower modes.
No, you will still have supersymmetry for the massive modes. You have an equal number of bosons and permanents at every mass level.
Okay.
Can you comment something on the dimensionality of fields? That you have these dimensionful couplings for the...
So when you change dimension, it's true that V has dimensions because it carries dimensions of the 6 x's that you compactify. So for example, if you start with...
But even before...
When you do super-Yang-Mills, you have a 1 over G squared. So when you do dimensional reduction, the 1 over G squared gets multiplied by this V. So the dimension of G changes. If that's what you're asking. So in 4 dimensions, for example, G doesn't have dimensions. But in 10 it does.
So when you write this covariant derivative,
yes,
it has a derivative, an ordinary derivative, and
there's always two choices. You can either write del as D plus G times A,